like collectively try to give you the benefit of the doubt in regards to due dates and extra exercise and stuff like that, because I want to make sure that nothing schedule-wise impedes our collective ability to get the assignments done. Now, if you're a person that says, well, I'm just going to do it, then I'll go back and ask for extra time then no, that's not going to happen. But collectively, if it's a problem for everybody, then I'll obviously work with you. Picking up with 1.5 though the other day, we kind of worked through some of these vocabulary words, but I want to talk about them as kind of what we're doing here. We're developing adjectives, right? Okay. Adjectives describe nouns, right? Okay. So if I was to define or sort of describe, Lex, I would say smart. I would say a good athlete, fast. Okay, that kind of stuff, right? Good decision maker. Okay, those are adjectives to describe him, right? Okay. If you guys were describing me, smart, good looking, all those types of things, right? Yeah. Okay. And you can have, my point is that you can have multiple describers, multiple descriptors, or descriptive words for an object. So when I talk about adjacent angles, I'm not saying that that's the only thing they could be. Okay? It's just one characteristic, one way of describing that set of angles. Because they could be adjacent, and they could also be complementary, couldn't they? Are 1 and 2 adjacent and complementary? Alright? But they could be just complementary. They don't have to be adjacent as well. So A and B, they're just complementary. Alright? So something that's important with our vocabulary words is the idea that obviously the words that we use and the words that are written are important to us. But the words that we don't use are as important as well. And what I mean by that is, in that phrase, in that definition, complementary angles are two angles whose measures have the sum of 90. Nowhere up there do I use the phrase that they have to be adjacent, or that they have to be coplanar, or that they have to be non-adjacent, or anything like that. Does that make sense? So it leaves the door open for all those things to exist for complementary angles. They could be adjacent. They could be non-coplanar. They could be non-adjacent. Does that make sense, everyone? Okay? So the way we read our statements and we interpret them, the information that is written is extremely important, but we also got to kind of understand the things that are not written. Okay? And the deletion or the leaving out of some of those phrases allows us to interpret the different varying situations that we could have. Right? So I think that's very, very important. We talked about complementary being the two angles, had to be two angles that have to 90 degrees, right? That was the last thing we stopped on. What I want you guys to understand is that when I have angle 1 there, let's say angle 1 is 30 degrees. Angle 1 is 30 degrees, and angle 2 is 60 degrees. Okay? So one of those is 30, one of them is 60. What we refer to those as is angle 30 is the complement of 60. Okay? And 60 is then the complement of 30. Alright, so both of those can be referred to as the complement of the other angle. Is that okay with everyone? We made an analogy earlier today. Let's say that me and Ty are brothers. Okay? It'd be like a lifelong dream come true for Ty, right? Okay, so if we're brothers, he would call me brother, right? Or consider me a brother. But on the other hand, I could call him a brother, right? It's a two-way street when you're a sibling, right? Okay? When we talk about complements, there's two angles being discussed here, and they're complements of each other. All right, so it's kind of that brother-brother aspect. Okay, and I think it's important for one of the questions, or a couple of the questions that we see in our homework, that hopefully we have time to talk about here towards the end of the period. But angle 1 is the complement of angle 2, and then we can reverse roles and say angle 2 is the complement of angle 1. The nice thing about these is that we know by definition it has to be two of them, and we know that they total something. So if I give you one of them, you can use subtraction to find the other one, right? So I'll tell you angle 1 is 40 degrees, don't you automatically know through the use of the total of 90, the measurement of 40 that I gave you, that the remaining one is 50? You can do that subtraction pretty quickly. And that's something that we're going to try to target a lot in this class, is if I give you a total, let's say I give you 5 things in a total, okay? Or we have 5 objects in a total, and I define 4 of those for you, you should be able to use subtraction to find the 5th one, okay? And that happens a lot in this course. Something else that happens a lot is that once we learn one concept, like complementary, a lot of times we have a very similar concept, and we change it just slightly. Okay, we talk about complementary being 2 angles that total 90. Now we talk about supplementary, and supplementary meaning 2 angles that add up to 180. Again, has to be 2 angles. Again, we leave out phrases like they have to be adjacent, or they have to be coplanar, or they have to be non-adjacent, or something like that. Okay? They could just be any 2 random angles in any location compared to one another, any orientation compared to one another. As long as they add up to 180 degrees, we classify them together as a group to be supplementary. So there you see the 30 and the 150, obviously non-adjacent. They do not share any vertices or common rays, and they would be supplementary. Their total is 180. If I look down there on the bottom right, angles 3 and 4, because they form a straight line there, right? Would you see that horizontal line there with 3 and 4? This here, that's a straight line, right? Straight angle. Okay, so that's 180. So now we're saying, well, 3 and 4 add to 180, using the angle dishwasher, all that kind of stuff. So we would say that those 2 angles are supplementary. Is that okay? If I look at B and C, 137 plus 43 gives you 180 as well. Those 2 angles would be supplementary. And that's kind of a variation, a variety of different ways of seeing those angles that are supplementary. They do not have to be touching. They do not have to be on the same plane. One could be on your book. One could be on the ceiling. We talked about that last week. It doesn't matter as long as they add up to 180. Is that all right? Okay. Again, we use the word supplement to talk about them. Okay. 50 is the supplement of 130. 130 is the supplement of 50. Come on. All right. When we start looking at period, I think this is just it might seem like it's kind of out of place here in this problem or this PowerPoint, but I think it's a good time to start talking about this stuff. We've mentioned it a little bit, but it's the concept of what we can find from a diagram, and the conclusions or the assumptions that we can make from a diagram. The one thing I want you to make sure that you understand is that assumptions put you in a bad spot. Okay? Think about this: if it's late December and I'm out next to a pond and it looks like it's frozen over, that's an assumption that I'm making. And let's say that I walk across it. Is it a very good assumption or a safe assumption? Probably not, right? Even though it looks frozen, it might not be thick enough to hold my fat body, right? Okay, it might fall through, right? Okay, shake your head like that. All right, so the idea here, guys, is that assumptions are going to get you in trouble. If it looks like they're congruent, you don't want to say that. You don't want to say that based off of looks, I can reach a congruency or an equality argument. For instance, if I give you this picture here, A, B, C, and D. And I tell you, look at A, B, and look at B, C. They look the same, don't they? Or somewhat the same. We don't want to make that argument until they provide us notation that they are. Or somehow through a definition or a vocabulary word or some other postulate or rule that tells me I can make an argument of why those 2 things are equal. Does that make sense? Do not go off of just what it looks like, okay? You've all made, in your life with your friends, your family members, whatever, you've made conclusions about something or someone before you had enough information about them, right? Okay? And when you make those conclusions about that person or that action without having enough information, in the end, you usually end up being wrong and you look foolish, right? So that's the same thing you want to think about here. Don't start making assumptions, because in the end, those assumptions are probably going to be wrong and you're going to look foolish at the end, okay? There's only a handful of things that we can assume from a picture. Okay, and I'm going to give you 3 of them right now. There might be 1 or 2 that we add in the next 160 days that we have together. Those are the only 3 that we want to talk about. Angles are adjacent. That's something I can look at in a picture. Okay, I can look at this picture right here, and I can tell you that that angle right there and that angle right there, so DBA and DBC, they're adjacent. Because the definition for adjacency is kind of a visual cue to begin with. It says, do they have the same vertex? Check that off. Do they have a common ray? Check that off. Do they have overlapping points? Check that off. Okay? And that can guarantee them that I have adjacency, right? Does that make sense, everybody? Okay? The same thing happens when I get to option 2 there, bullet number 2. It says angles are adjacent and supplementary. Okay? Would you agree that angle 1 and angle 2 are adjacent? We can check off those things, right? Common ray, common vertex, no common interior points. Okay? Can you also visually tell me that angle 1, that ray right there for angle 1, and that ray for angle 2, they make a straight angle. And straight angles total what? 180. So we can kind of make a progression here from the picture saying straight angle means 180. So that straight angle of 180 is being made by angles 1 and 2, right? Add angles 1 and 2. So now you got 2 angles being added together, and they should total 180, right? What does that mean? What do I have? What vocabulary word do I have when I have 2 angles that add up to 180? Supplementary. Good. Okay. So that's why we can visually say I have supplementary angles when they're adjacent, or I can visually determine adjacent and supplementary angles. Okay. Now I can't do that here. If I give you something like this, those 2 angles, we cannot make the argument about them being supplementary in this case because they're not adjacent to begin with. Does that make sense? I need that and part. I need both pieces of criteria. And then I can make that argument from a picture. Angles are vertical. Again, angles that are vertical, the way they're defined is kind of like an existence definition. Meaning this is how we create them. So if I can kind of trace over, I tap with that one, there we go. If I can trace over that line that creates angle 1, okay, and I don't want to just look at the ray that creates angle 1, I want to look at the line. And then I look at the other line that helps create angle 1. Would you agree that the red line and the blue line help create that angle? Do they at the same time help create angle 3? And that's what we mean by vertical angles, right? Angle 1 and angle 3. So if you can do that, if you can trace them out like that, visually speaking, you are showing that you know what the definition of vertical angles are and how you can locate them and identify them. Okay, so you can do that through a picture. You do not have to be provided information that says 1 and 3 are vertical. The picture's enough to do that. And throughout the whole course, guys, those 3 statements are really about it in regards to what you can conclude from a picture. Okay? Now, the things right now that we cannot conclude from a picture are those 3 bullets at the bottom. And that's just because we haven't talked about a whole lot of things, but that list will turn into like 100, 200, 300 things. Okay? And obviously we won't continue to add to that list and write all those things down. But the idea is that you're not going to be able to make assumptions like this until you have critical criteria that tells you you can make a valid statement. Okay? If I look at this, I do not want to deal with this second bullet first. I do not want to say that's a right angle. It might look like it, right? But I do not want to make that argument until somebody puts that notation in there for me. Maybe they tell me, you know, if that's A, B, and C, maybe they tell me that BA is perpendicular to BC. Okay? Then I could use the information that angle is a right angle. Does that kind of make sense? There are different ways that they can provide me, or they can imply that I have a right angle, but just by looks, we can't do that. All right? And a lot of times we go off looks because we think that's going to be easy. It's what we would want. We would want, maybe in this picture, right here, for that to be a right angle. But we got to have a progression of thoughts and logic and reason that says it's a right angle, and we can argue that and be kind of foolproof with that. It's like the argument with, if I'm being convicted in court over a crime, and my lawyer just says, Mr. Fay did not do it. I may 100% not have done it, okay? But is that going to get me free? If that's his argument that he just didn't do it? Or is the the prosecutor going to come up and say, these are the reasons why we think that he's done it? And we logically can put together an argument of why we think he's guilty. If that argument is a little bit better than my argument or my lawyer's argument, am I going to jail? Even though I didn't do it? Does that kind of make sense to everybody? Okay? So just saying something, we don't want to do it. Just assuming by a picture we want to do it. We want to have a valid argument that you can say, I know with 100% certainty that that's a right angle. Without that information, you cannot do that. Okay? Angles are complementary. That kind of goes off the same idea. Okay? Because complementary, the aspect of complementary means I need 90 degrees first, right? So if I just do something like that, angle 1 and angle 2, even though that red angle looks like a right angle, I don't want to say 1 and 2 are complementary because I don't know if that's truly 90 degrees. Does that make sense? I still need that box in there. I still maybe need something like that. Okay? And that's kind of what we're going to do throughout the year is we're going to come up with rules. We call them theorems. Okay? Some of these postulates are doing the same thing where it allows us to kind of connect the dots in regards to, okay, this is the information I'm provided. How does that lead me to that red angle really being a red angle or a right angle without them telling me with the box? Does that make sense? Okay. In that top one, angles or segments are congruent. These segments that I have drawn up here, they look congruent, but not until they tell me that 100% with notation that they're congruent. Can I say that? Or maybe they tell me with vocabulary, with midpoint, or something like that. So there's a lot of stuff, guys, that you're going to want to say is happening or is true. I want you to kind of fight against doing that until you know for certain. Okay? If there's ever doubt, okay? If there's ever doubt in your mind of whether you can say it from a picture, don't say it. Right? If there's ever doubt in my mind whether I should walk across that ice, I probably shouldn't walk across it. Right? Okay? And that's going to be the safe thing for us to do. All right, so I'm going to give you a picture here, and I'm going to ask you some questions about it, and you're going to tell me what you think. First thing I'm going to do is get rid of these marks. All right, so look at angle 1 and angle 2. Can you tell me, look at them, look at them real close. Can you tell me that they're congruent? You can't. Okay? Because there's no notation, right? Okay? The only way that I can tell you, that you can tell me is that they're congruent, is if I gave you that notation right there. Right? Okay? Or if I said something like that, maybe I got like point B and C, and maybe I say that, well, this X and Y. Let's say that I say BC, that ray, so that's this ray right here, bisects angle XBY. Then, if I didn't have this notation in there, okay, so I take the notation out, but I give you this phrase here. Now can you tell me 1 and 2 are congruent? Because we know what bisects means, right? Okay. So there are things that are hidden inside vocabulary words and things like that that we're going to use to make decisions. But if I don't have any of that stuff, I don't know what just happened there. If I don't have any of that stuff, and I just have this picture, even though they look like they might be able to be cut and pasted and set on top of one another, we cannot make that argument until the notation is provided. Is that all right? What about 3 and 4? Is there anything that you can tell me about angles 3 and 4? They're supplementary, okay? Because we have the adjacency, okay? They share that vertex, they share that ray, okay? They are adjacent, and together, they form that straight line, right? That straight angle is 180 degrees. Adjacent angles that add up to 180 degrees are supplementary, okay? 3 and 4 supplementary. Can I say the same thing about 4 or 5? Yeah, should be able to. What about something like angle 3 and angle 5? What can I say about those? Okay. They're vertical. Okay? Because the lines that make them, if I trace out the lines that make angle 3, that line right there, does that help make angle 5 as well? And if I trace out the other line that makes angle 3, it also helps make angle 5. So now that angle and that angle are by definition vertical. And we can see that through a picture. Okay? Is that okay with everyone? Can I say 1 and 2 are adjacent? Can I say 1 and 5 are adjacent? Okay, those are all things I can't say. Can I say 2 and 5 are non-adjacent? Yeah, because they don't share a common side, right? Or, I guess that's the only thing they don't share. They have a common vertex and a common interior. So there are things that you can say about a picture, things that you cannot say about a picture. I want you to make sure that we understand that kind of inside and out. Okay? You're going to fight that all year long. It's going to be, I will hear people say all the time, well, I did this because they looked like they were equal. And I'll stop you right there and I'll ask you to repeat yourself. And eventually you'll figure out, well, that's my problem. I need something else. I need some vocabulary or some other relationship that allows me to make maybe a different argument than what I made. All right, that gets us to this. This is probably one of the most important postulates that we will cover. And it's pretty straightforward, it's pretty simple. But it allows us to build a lot of concepts about triangles. And those concepts that allow us to build triangles allow us then to build other shapes, which ultimately gives us kind of our collection of two-dimensional shapes in geometry, which then we piece together, get three-dimensional shapes and a lot of kind of stuff. So this is kind of a very, very critical part of this course, and it's talking about a linear pair. Okay, pair meaning two, linear meaning line. Okay, still talking about angles here. Okay, so it's a type of angles or type of pair of angles in which the non-common side, they're adjacent, that's key, but their non-common sides are opposite rays. Their non-common sides are opposite rays. All right, so those two rays that I just drew up there, they're the non-common sides. They're the sides that are not shared. The sides that are not overlapping. BD, that ray would be the common ray. Okay? But if the non-common sides form a straight angle, then you've developed what we call a linear pair. Okay? Pair of things that form a line, right? Those things being angles. That picture right there, what I want you to understand, what I need you to understand, is the same as that picture right there, isn't it? Which is the same as that picture there, correct? Everybody kind of visualize that? Which is the same as maybe that picture. Which is the same as that one. It's the same as that one, okay? So whenever you're seeing this picture right there, and that's kind of the way it's usually defined for us, we're talking about all the different variations of that, where D could be anywhere on the top of the black line, the bottom of the black line. The black line could really be any slope that it wants to have, okay? But those are considered linear pairs, okay? And together they always form that line right there, okay? So if that line, we talk about them opposite rays, okay? But when we have a pair of opposite rays, it creates a straight line, right? Which we also refer to as a straight angle, correct? How many degrees are there in a straight angle? 180. Okay, so let's use the angle addition postulate. That angle there and that angle there, 1 plus 2, okay, should equal this straight angle, right? Should be equal to 180. Well, what's another word for two angles that add up to 180? Supplementary, okay? So the way we can piece this together says, okay, a linear pair is always going to be two angles, right? And it's always going to be that picture right there. So they're always going to be supplementary, correct? So we get the postulate. One of the key postulates of this course. It's called the linear pair postulate. If you want to remember it by that name, that's fine, but you also need to know what's inside that name. It says if two angles form a linear pair, then they are supplementary. If two angles form a linear pair, then they are supplementary. And then I want to ask you a question. True or false, linear pairs are supplementary. Is that true or false? That's true. True or false? Supplementary angles are linear pairs.
False.
False. Okay? Because supplementary just means what?
Automatically equal 180.
Okay, two of them add up to 180, right? So I go back up to this picture right here. B and C, they are supplementary, aren't they? Are they forming a line though? No. Okay? Now this would be a situation where that does happen, but based off what we know about supplementary, that orientation of 3 and 4 does not have to exist for things to be supplementary. Linear pairs have to be supplementary. Does that make sense? But supplementary angles do not have to be linear pairs. Because supplementary angles, does it say they have to be adjacent up here? No. Linear pairs. Does it say they have to be adjacent? It does. Okay? So that's the idea. That's what allows us to say true or false when those linear pairs are supplementary. Absolutely. That's exactly what that postulate is saying. Okay? Supplementary angles are linear pairs. Sometimes that's true, sometimes it's not. So if I say true or false, then we're going to go with false. Okay? I go always, sometimes, or never. You'd say sometimes. All right. Does that make sense to everybody? All right. So then when they bring in these rules that have, a rule that says supplementary, and we know supplementary by definition leads us to the idea of adding to give you 180. Well, adding to give me 180, that's an algebraic concept. So we're probably going to practice that at some point, and that's what this question here is targeting. It says angle KPL and angle JPL are a linear pair. So I read that and I see that vocabulary word, linear pair. Okay, now I know vocabulary-wise what that's going to look like. Okay, and now with the postulate, the linear pair postulate, that word right there is giving me a relationship. I'm going to take two angles and add them together and set them equal to what? 180. That's the overall general relationship here. And those two angles are going to be KPL and JPL, right? So I'm going to take KPL, which is 2x plus 24. Add to it JPL, which is 4x plus 36. And that should total 180. Okay. You guys remember, I was probably 3 or 4 days ago, I give you something similar to this, but instead of saying a linear pair, they would say something like KPJ was a straight angle. Okay, and then you say, okay, well, what two smaller angles are adding up to give you that straight angle? You would find those two things and then add together and set them equal to 180, right? This is essentially saying the same thing if you had a picture. I don't need a picture, but I could put a picture on. If I look at KPL and JPL, what parts are they sharing? What letters do they share? KPL and JPL. They share what? P and L, right? Okay. So that must be the common side. So I'm just going to draw P there. Maybe L is there. Maybe K is there. Maybe J is there. Does that make sense? Okay, that satisfies what's going on there. They're a linear pair, KPL, JPL. There's no distinction that K has to be to the left of P or J has to be to the right. So if you put J here and K there, it gets you the same results. But now if I look at this, KPL is 2x plus 24. 2x plus 24. This one here is 4x plus 36. Plug that in. And last week we said KPJ was a straight angle. Well, we're really getting at the same thing when we say that KPL and JPL are a linear pair. Does that make sense? It's really two different ways of saying the same relation. If this was a straight angle, we'd say that angle plus that angle equals 180. 2x plus 24 plus 4x plus 36 equals 180, and it gets me the same exact thing I got there when I talk about linear pairs. Okay. Adding either one of these up, you're gonna get 6x plus 60 is equal to 180. 6x equals 120. X ends up being 20. Hopefully you guys did that and you figured that out, right? Not too hard in regards to the algebra. When I go back and I plug things in, it tells me one of those angles KPL is 64 degrees, and the other one JPL is 116 degrees. 64 plus 116 gives me my 180, right? Okay. So that's important, that's useful. The last definition I want to give you, and then we'll go over a couple of questions from the homework, is this here when we're talking about angle bisectors. Okay? An angle bisector is a ray that divides an angle into two congruent adjacent angles. We're going to be focusing on the idea that if I start splitting objects up, I split a line up, or sorry, a segment. When I split a segment, I get smaller segments, right? Okay. You know, when you're in science and you split a cell, you get two more cells, right? Okay. You know, I don't split a cell and then get, I don't know, a TV. That doesn't make any sense, right? Okay. When I split cells, I get cells. When I split segments, I get segments. When I split angles, I get angles, right? In the past, I get a lot of people say, when I split an angle, I get an angle and a segment. Or when I split a segment, I get a segment and a line. All right? You get smaller objects that are relatable to what you started with. Okay? But the relation between those smaller objects, the two smaller objects, should be equal to one another. So a lot of times you're going to see a picture like this. There will not be notation in it, but they will give you this phrase right here. They will say that ray GH bisects angle FGI. Well, then we need to realize that bisects means it creates two congruent angles. They got to be adjacent. So that identifies then that angle there, FGH, and this angle here of HGI. And if they're congruent, what's that tell me about that measurement compared to that measurement? Be equal, right? 3x minus 3, set that equal to 4x minus 14. I'll let you solve that, but that's what we're targeting when we use this angle bisector. Okay? Because what happens, guys, is that they want us to mess around with this type of equation a lot in this picture, but they don't want to, every time they give us this picture, give us those two red marks in there. They want to give us this relationship that I've got an angle equal to an angle, or a measurement equal to a measurement, but they don't want to give me the same route or same pathway of determining that equality every single problem. So sometimes they'll give me the picture and they'll put the notation in. Sometimes they'll take the notation out and they'll give me that phrase. Okay? Sometimes they'll take both those things out and give me a different phrase. It leads me to the same thing, and we'll talk about that later on. Okay? We've got to be able to interpret that vocabulary. If I don't know what bisects means, can't do this problem, right? Okay? If you don't know a lot of these vocabulary words in this first chapter, you're going to be swimming for a long time in this course. Okay? All right. There were a handful of questions in your homework that I want to talk about. 13 and 14 were like this. And then I believe the last couple, 23, 21, 22, 23, kind of in that ballpark. We'll talk about those as well. All right, so this one says, using an algebraic equation to find the measure of the two angles described below. It says, begin by letting x equal or represent the degree measure of the angle supplement. If you remember back to Algebra 1, you did this type of stuff, okay? They gave you word phrases, and you had to convert those word phrases into algebraic expressions. This is one of those reasons, and we're now using the same algebra concept, but now there's some geometry context to it, so we can actually see that algebra at work in a useful way. What I'm worried about with this question, and what I'm seeing a lot of people do, is that they just grab their calculator and they start doing work on their calculator. They write stuff down on the paper, but they're not very organized in their work, and they're not very descriptive in what they've let variables be. Therefore, when they answer this question, they answer it backwards. Okay? Because there's two components, I think, to this question. There's two answers you're going to get, and it's very easy to get them backwards. So what we're going to do is we're going to write down, we're going to let x be, we represent the angle supplement. That's what they tell me, right? And the reason they choose this, that x be the angle supplement, as we read our description, the angle supplement is the thing that we know the least amount about. We don't know a whole lot about the supplement angle here in this problem. If I read this, it says the measure of the angle is 29 times greater than its supplement. The measure of the angle is 29 times its supplement. So this must mean that I'm talking about the angle here. And how am I going to write it? 29x. Okay? And that's what I'm saying is that I don't know much about this. I don't know much about the supplement. But they told me a lot about the angle, right? They told me how to write the angle in regards to the supplement. So I let the supplement's the thing I know the least amount of information about. So that's what always let me be my simplest variable. Okay? If I reversed it, it's going to be a very problematic way of setting up these. Okay? So, I could let this be 29x, but it makes this look a lot uglier, vice versa. And then the algebra that's involved in solving would be a lot harder. Okay? So this, I think, is the best way of doing this. It says the measure of the angle is 29 times greater than its supplement. So how do I relate those? I've defined them. I know what they are now. Their sizes compared to one another. But how do they relate to one another? What kind of equation would I set up?
When added together, they equal 180.
Good. Because it says supplement, right? Supplement refers to the idea of supplementary angles. So I'm going to take these two things and add them together. That gives me 30x. I'm going to add those two together. I should total 180, right? So now x is going to be 6. If x is 6, that's what this angle measurement here is, right? If that's 6, this is the supplement. That's going to be 174. If I did not write this stuff down, guys, a lot of people are writing this. They're plugging in right here. What they want is a supplement. They want 6 right here. A lot of people are typing in 174, which tells me you did everything right. You just weren't paying attention to what you were finding when you solved things. Does that make sense? Okay. So you get your two answers backwards, which obviously is wrong. Probably on a homework, I would go back and give you credit for it. But in a course exam, it's wrong. Okay. Even though you've got everything right, a little bit of algebra confusion there in describing my parts. And they're going to consider me kind of a bad geometry student because of that. Is that okay? All right, you see something, I think, on 14 in regards to complementary, and it's really just the same type of question. The last couple look like this. Anybody get to these and not really know what to do? There's a lot of relationships up there in that picture. A lot of them are useful. A lot of them create extra work that maybe we want to avoid. And there's also a lot of relationships up there that we haven't even described yet and talked about in this course yet. But the first thing I want to look at is maybe the long way of doing this, maybe the incorrect way of doing this that I think gives you an appreciation for the short way. If I look at, let's just say, that angle and that angle, those two green angles, what's a relationship that you know about them? They're supplementary. They're a linear pair, right? Linear pairs are supplementary. So I could add those. So 3y plus 10 plus 2x plus 6 should equal 180, right? Why is that equation problematic? Maybe why is it different than the other equations we've dealt with so far all year, Ty?
It has 2 different terms.
Yeah. Got that y and that x, right? Got two variables. Anybody know what we need to do if we have an equation that has two variables in it? Okay, I can solve for one of them, so solve for y or solve for x, right? But then and you're right, I need to plug it back in, but I can't plug it back into what I have, because it's not going to lead me anywhere. I need another equation with the same two variables to plug back into, okay? So something that we could do is say maybe we look at that angle and that angle, right? Are they a linear pair as well? So maybe I write 3y plus 26 plus 3x minus 56 equals 180. Okay? Now, you're 100% right. We could solve for x or solve for y in either of those and plug in the other one, and that's the substitution method. But maybe you guys remember this. Can I take and rewrite this as 3y plus 2x? So I'm done with that, done with that. Move my 16, that's I get from here, to the other side, and give you 164. Okay? That says the exact same thing that does. Can I take that one, do the same thing, 3y plus 3x. That and that are going to give me negative 30. Move that to the other side through addition, gives me 210. You guys remember doing something like this? That's called the elimination process, right? And I just think this is a little bit quicker than the substitution process. We'll get there, but you're right. If I go this approach, I want to hopefully add straight down and get my variables to cancel out, right? 6y, 5x. It doesn't happen. So you go through and you multiply everything by some constant, right? Negative 1 in this case. Cancel out, gives me x. Add straight down, gives me, what's that, 46? And now I've solved for x. Does that make sense to everybody? Was that a long process? I'm only about halfway done because I got to plug back in and solve for y. That's elimination, and that's perfectly fine, that works. But that takes some time. I think some of you are seeing this. What's the relationship between those two angles? They're supplementary again. They're a linear pair again. But what is nice about looking at those two? One variable. They're going to add together and leave me with just y, right? So I'm going to solve for y pretty easily. And that would be pretty quick to do. What about those two? Same idea, right? One variable solves for x. And what I'm trying to get at here, guys, is that when you are doing these problems in geometry, okay, there might be 3, 4, 5 different ways of doing it. I want you to, before you just look at the problem, just start haphazardly going about it and not thinking about what you're doing. Take a second. Take 10 seconds, 20 seconds. Think about what your options are and foreshadow a little bit about what the math that's involved in those options. When you read an English book, don't you read a couple chapters in the foreshadow, think about what's going to happen? Or you watch a TV show, okay, I'm trying to find out who the killer is in this show or something like that, right? You foreshadow that all the time, and as things are changing, you're continually changing how you foreshadow, right? Same thing in math. Before you do anything, think ahead of the amount of work that's going to involve for you, okay, and the different options. All my tests are written so that you can finish them in 45 minutes, okay, or shorter. But if you're a person that, when you see this problem 3 or 4 times on a test, and you do system equations every single time, you're going to run out of time. The ACT, 60 questions, 60 minutes. If you go the long route on all those questions, you're going to be bubbling in about 35 questions when there's 2 minutes left. Okay? Math is a great thing to explain a lot of phenomenons, but a big aspect of the reason we do a lot of the things that we do in math and the processes is to eliminate wasted time, to become efficient and to be fast at coming up with solutions. That's why we have a lot of our postulates and theorems and stuff like that. So keep that in mind as we go through some of these problems throughout the year. 1-5, due Wednesday. Okay, I started class on Wednesday. Got the S-Fest tomorrow.